Hey everyone, and welcome to another deep dive. You know, we love to explore the cutting edge of science, and today we're going on a journey to the nano universe.
Yeah, to a place where the seemingly impossible becomes a reality.
And you know, the place where we can actually see things thousands of times smaller than a human hair.
It's pretty mind-blowing.
It is. And you shared this awesome article with us from scitechdaily.com.
Oh, yeah.
Called Unlocking the Nano Universe, a quantum leap in magnetic imaging. And I think that title really captures the essence of this research.
It really does.
Because it is a quantum leap forward. And I have to say, I was so captivated by this research from Martin Luther University, Halle-Wittenberg, and the Max Planck Institute, because they basically figured out how to see the invisible. And you know what that means?
What's that?
It means advancements in data storage.
Of course.
Electronics. Medicine. The implications are huge. But before we get ahead of ourselves, let's break down what they actually accomplished.
Yeah, let's do that.
All
Let's
right.
start with the basics.
Yeah, so they can analyze magnetic nanostructures with insane precision.
Right.
Like we're talking a resolution of 70 nanometers.
70 nanometers, which is incredible when you think about it because
It's tiny.
it is tiny. Traditional optical microscopes, even the most powerful ones, can only go down to about 500 nanometers.
That's a huge difference.
It is a huge difference.
So they basically shattered this resolution barrier.
Yeah, they've blown it wide open.
But how do they do it?
Well, that's the really interesting part, right?
All right. The article mentions this thing called the anomalous Nernst effect, or ANE.
Yeah, the ANE.
I have to admit that sounds a bit intimidating.
It sounds very complex, but it's actually a pretty simple concept when you break it down.
Okay, so break it down for me.
Okay, so you know how thermocouples work?
I think so.
Okay, so you have two different metals joined together, and when you heat one junction, it generates a voltage.
Okay.
The ANE is similar, but instead of two metals, we're talking about a magnetic metal and a temperature gradient.
Okay, so it's like using heat to reveal the magnetic secrets hidden within these tiny structures.
You got it.
I like that.
It's a really elegant way to probe magnetism at the nanoscale.
But how do they make it work at such a small scale?
That's where the real ingenuity comes in.
Okay, tell me.
They pair this principle with an incredibly sharp metallic tip, almost like the kind used in atomic force microscopy.
Oh, wow.
And by focusing a laser beam onto this tip,
Okay.
they create an incredibly localized temperature difference right on the sample surface.
So they're using the laser in the tip like a microscopic soldering iron.
Exactly, creating this tiny hot spot on the sample.
And that triggers the ANE.
You got it. But here's the really cool part. The metallic tip also acts as an antenna.
An antenna. What do you mean?
It concentrates the electromagnetic field in that tiny region.
Oh, wow.
Amplifying the ANE signal and making it much stronger and easier to detect.
So they're combining this subtle thermal effect with this clever way to amplify the signal.
Right.
And suddenly you can see things that were impossible to see before.
Exactly.
And that's how they were able to visualize a magnetic vortex.
That's right. That was one of their key demonstrations.
What does that even look like at that scale?
Picture a tiny whirlpool, but instead of water swirling around, it's the magnetic moments of the atoms aligning in a circular pattern.
Oh, wow. So they're mapping out these invisible magnetic tornadoes.
That's a great way to put it.
That's so cool. Why is that so important, though?
Visualizing these structures is crucial for understanding how they behave and how we might be able to manipulate them.
I see.
And this is where things get really exciting because it opens the door to a field called spintronics.
Spintronics. Okay, that sounds futuristic. Tell me more about that.
So instead of relying solely on the charge of electrons, like in traditional electronics, spintronics harnesses the spin of electrons, their intrinsic angular momentum to carry and process information.
So imagine electronics that are smaller, faster, and way more energy efficient.
Exactly. We're talking about a potential paradigm shift in electronics.
Okay, now I see why this is a big deal. We're not just talking about, incremental improvements. We're talking about revolutionizing the entire foundation of electronics.
Right. And it all stems from being able to see these tiny magnetic structures.
That's amazing. It's like this tiny little discovery has opened up this huge world of possibilities.
It really has.
And it's not just spintronics, right?
No, it's not.
There's also implications for data storage.
Absolutely.
And this whole new class of electronics based on these things called chiral antiferromagnetic materials.
That's right. Chiral antiferromagnetic materials are another exciting area where this research could have a major impact.
Okay, so we've got spintronics, we've got data storage, and we've got these chiral antiferromagnetic materials.
We've got a lot to unpack here.
It sounds like this research is touching on some seriously cutting-edge areas.
It is, and the implications are far-reaching. But before we dive deeper into those specific areas, maybe we should take a step back and explore how this new imaging technique actually works in more detail.
I am all for that. I'm already hooked on this story, and I want to know more about the science behind it.
Okay, great. Let's start by unpacking the anomalous Nernst effect a bit further.
Okay, I'm ready.
So it all begins with a magnetic metal. Imagine it like a tiny, tiny bar magnet. And if you apply a temperature difference across this mini magnet,
okay,
like one end is warmer than the other, something fascinating happens. You generate a voltage, but not just any voltage. It's perpendicular to both the direction of the heat flow and the magnetization of the material.
Whoa, okay, so I'm picturing like a tiny magnet getting a bit warmer on one side and suddenly zap, a voltage appears in a completely unexpected direction.
That's a great way to think about it.
Like a magnetic party trick or something.
Yeah, kind of like that.
But how does that translate to seeing these nanoscale structures?
Right. So remember that super sharp metallic tip we talked about?
Yeah.
They focus a laser on it, which creates an intense but incredibly localized temperature gradient right at the tip's apex. So you're essentially heating up a spot on the sample that's only a few atoms wide.
So like a microscopic soldering iron.
Exactly. Creating a tiny hot spot on the sample, and that hot spot triggers the ANE in the material right beneath the tip. But here's the ingenious part. The metallic tip also acts as an antenna.
An antenna. Okay, I'm listening.
It concentrates the electromagnetic field in that tiny region, amplifying the ANE signal, making it much stronger and easier to measure.
So they're listening in on the magnetic whispers of these tiny structures by amplifying the signal with this antenna-like tip.
That's a great analogy. And that's how they were able to visualize a magnetic vortex. Remember we talked about that?
We did.
Mapping out its intricate details. These magnetic vortices are fascinating things.
They are. I mean, I'm picturing these tiny magnetic tornadoes.
It's a good way to visualize it. They have this unique swirling pattern of magnetic moments, and understanding their behavior could be a game changer for data storage.
Oh, yeah. You mentioned that earlier. How could they play a role in data storage?
Yeah. Well, imagine storing information in the direction of the magnetic vortex core.
Okay.
A vortex spinning clockwise could represent a 1, and counterclockwise a 0.
Whoa, so we're talking about storing data in the spin direction of these tiny magnetic tornadoes.
Exactly. It's a mind-boggling concept.
It really is. And what about spintronics? How does this imaging technique help advance that field?
So to develop spintronic devices, we need to understand how electron spins behave at the nanoscale, how they interact with each other and with their environment, and this imaging technique provides us with a tool to do just that.
So it's like giving researchers a powerful new microscope to peer into the world of electron spins.
Exactly. They can now study these tiny magnetic structures, how they form, how they interact, and how we might be able to control them.
That's amazing. So we've covered spintronics data storage. What about these mysterious chiral antiferromagnetic materials? What makes them so special, and how does this new technique help us understand them better?
Okay, let's break it down. Chiral refers to a type of asymmetry. Imagine your hands. They're mirror images, but you can't superimpose them perfectly.
Yeah.
That's chirality. And antiferromagnetic materials have their magnetic moments arranged in opposite directions, effectively canceling each other out at a larger scale.
Okay, so they have a unique handedness and a hidden magnetic order. But why are scientists so interested in them?
Well, these materials have the potential to revolutionize electronics. They could lead to devices that are even faster and more energy efficient than what we have today. The challenge is that their unique magnetic properties are notoriously difficult to detect with traditional methods.
So this new imaging technique allows researchers to finally see the magnetic order within these chiral antiferromagnetic materials.
Yes, it's like having X-ray vision from magnetic structures, and that's crucial for unlocking the potential of these materials.
It's incredible to think that this single imaging technique could have such a profound impact on so many different areas of research and technology, and it all stems from this seemingly obscure physical phenomenon.
Right.
The anomalous Nernst effect.
It really highlights the importance of basic research and how fundamental discoveries can lead to transformative technologies.
Absolutely. I'm curious, though, what were some of the technical challenges the researchers had to overcome to develop this technique?
Yeah.
Because it sounds really complex to build a system that can measure these tiny voltages with such precision.
You're right. It was incredibly challenging. One of the biggest hurdles was achieving the necessary stability and sensitivity to measure the minuscule voltages generated by the ANE. Remember, we're talking about nanowatts of power here.
Wow, that's tiny.
It is tiny. They had to meticulously design and fabricate the metallic tip, optimize the laser focusing, and develop ultrasensitive detection electronics to pick up these faint signals.
So it wasn't just about understanding the physics. They had to push the limits of engineering and material science.
Exactly. It was a truly interdisciplinary effort, and that's what makes this research so impressive. It's a testament to the ingenuity and perseverance of the researchers involved.
It sounds like this research is a major leap forward in our ability to explore the nanomagnetic world. But are there any limitations to this technique?
Of course, like any tool, it has its boundaries. One limitation is that it's primarily sensitive to the magnetic properties at the very surface of a material. It's not as effective at probing the magnetic behavior deep within the bulk.
Oh, I see. So it's like skimming your finger across the surface of a pond. You can feel the ripples and waves, but you don't know what currents are flowing beneath.
That's a great analogy. So while this technique is incredibly powerful for surface studies, it might not be the best choice for probing the inner depths of magnetic materials.
I see, but with clever sample preparation techniques, researchers can still use this to study a wide range of materials and magnetic phenomena.
Absolutely, and as the technology continues to evolve, we'll likely see further improvements in its sensitivity and capabilities.
It's exciting to think about what the future holds for this technology and the discoveries it might enable. Now, I know we've covered a lot of ground in this deep dive, but you mentioned earlier that this research is part of a larger initiative, the Center for Chiral Electronics.
Yes. The Center for Chiral Electronics is a collaborative research effort dedicated to exploring the potential of chiral materials for developing new and innovative electronic devices.
Right. So this research on nanoscale magnetic imaging is directly contributing to the development of these next-generation chiral electronics.
Exactly. By providing researchers with the tools to study and manipulate the magnetic properties of these unique materials, this imaging technique is paving the way for the development of entirely new types of electronic devices with unprecedented capabilities.
It really highlights how a single scientific breakthrough can have ripple effects across multiple fields of research and technology. The article mentions that the research was funded in part by the German Research Foundation as part of a program called the Collaborative Research Center Transregio 227.
Yes, the CRC-TRR 227.
Can you tell us more about that program and why it's relevant to this research?
Certainly. The Collaborative Research Center Transregio 227, or CRC-TRR 227 for short, is a multi-institutional research program focused on understanding and controlling the properties of strongly correlated electron systems.
Okay, strongly correlated electron systems. That sounds intense.
In these systems, the electrons are so closely packed together that their behavior becomes intricately turnway. Their movements and interactions are no longer independent, but highly correlated.
Oh, wow.
And these strong correlations give rise to some of the most fascinating and potentially useful phenomena in condensed matter physics.
So things like superconductivity magnetism and other exotic states of matter where the collective behavior of electrons takes center stage.
Exactly. And understanding and controlling these strongly correlated electron systems is one of the grand challenges in modern physics, and that's where this new imaging technique comes in.
It provides researchers with a powerful new tool to probe the magnetic properties of these complex systems at the nanoscale.
Precisely. And by studying how these magnetic properties emerge from the collective behavior of electrons, researchers can gain deeper insights into the fundamental physics governing these systems.
It sounds like this research is not only paving the way for new technologies, but also expanding our understanding of some of the most fundamental mysteries of the universe.
Absolutely. It's a beautiful example of how scientific exploration often leads to unexpected connections and breakthroughs across different fields of knowledge. And if I may, I think there's another intriguing aspect of this research that's worth highlighting. This research could really change how we think about magnetism as a whole.
Okay, how so?
We often think of magnets as these static objects, with a north and south pole. But at the nanoscale, magnetism is dynamic. Fluid and full of surprises.
So, like, we've zoomed in on a seemingly simple bar magnet and discovered a whole universe of swirling magnetic patterns.
Exactly, and intricate interactions.
It's funny, as we've been discussing this research, it's really struck me that it really highlights how interconnected science is.
Yeah.
I mean, we've talked about physics, we've talked about materials, engineering, Even a bit of chemistry. It seems like progress in one area often sparks innovation in others.
Absolutely. Science is rarely a solo endeavor.
Right.
It's a symphony of different disciplines.
Yeah.
Coming together, each contributing its unique melody to create something truly groundbreaking.
I like that, a scientific symphony.
Yeah.
And in this case, that symphony is leading to some pretty amazing possibilities.
It is.
I mean, from the potential of spintronics to revolutionize electronics to exploring new data storage paradigms and the development of these chiral electronics.
It's a really exciting time.
It is. It really is. And it all starts with being able to see.
Right.
To visualize these tiny magnetic structures with incredible detail.
That's the key.
It's a testament to the power of science.
It is.
And scientific tools and techniques to just expand our understanding of the universe.
Yeah.
From the smallest scales to the largest.
Absolutely.
It's truly inspiring, and it just makes me wonder what other hidden wonders are waiting to be uncovered.
Yeah.
With this new imaging technique. What mysteries of the nanomagnetic world are we just beginning to glimpse?
That's the beauty of science. It's an endless journey of discovery.
Yeah.
With every new tool, every breakthrough, we gain a deeper understanding of the universe and open up new avenues for exploration.
And who knows what incredible technologies and innovations might emerge from those explorations.
Exactly. The possibilities are endless.
It's an exciting time to be alive.
It is.
To witness these scientific leaps forward.
I couldn't agree more. As we delve deeper into the nano-universe, we're not just uncovering new knowledge.
Right.
We're also unlocking new possibilities for the future.
Well said. Well, on that note, I think it's time to wrap up this deep dive.
Okay.
Into the fascinating world of nanoscale magnetic imaging.
Yeah.
We've covered a lot of ground today.
We
From the intricate details of the anomalous Nernst effect to the vast potential of spintronics and the exciting promise of chiral electronics.
It's been a pleasure exploring this groundbreaking research with you.
Likewise, and I want to thank you, our listeners, for joining us on this deep dive. We hope you've gained new insights into the amazing world of nanoscale magnetism and the incredible potential it holds for shaping the future.
It's a field with a lot of potential.
It is. It is. And remember,
yes,
the universe is full of wonders waiting to be discovered. And often, the most profound insights are hidden in the smallest details.
That's so true.
So stay curious. Keep exploring. And who knows, maybe you'll be the one to make the next groundbreaking discovery.
You never know.
Until next time, happy exploring.